that the disk is made only of particles, condensed material, and they show that you can form a moon-like object in a on a timescale of an order of a year. However, there are several limitations to this model. First of all, within the Roche limit, you're going to have the combination of gravitational instabilities and tidal disruption that is going to lead to an increased rate of collision within the disk. And since each collision releases energy, you're going to heat up the disk so that on a timescale of a year, you would very rapidly vaporize such disk. Also, such fast accretion of order a year would imply that the moon would form completely molten, which seems in disagreement with some geophysical arguments, for instance, the lack of global force on the moon. So what we propose here is to study the dynamics of the accretion of the moon from a disk that would be here a fluid to represent the disk inside the Roche limit. What will be the accretion timescale and the influence of the disk thermodynamics? And can we find implication regarding the Earth-Moon isotopic similarities and the Moon's initial thermal state? So the concept model we have developed is represented here. You have the Earth obviously here, and we modeled the material within the Roche limit. What?
Use the pointer.
Oh yeah, that's right. That's better. Here. The disk inside the Roche limit is a uniform slab of material. While the disk outside is going to be represented by a collection of individual particles tracked with the n-body code Simba. And those two disks are going to interact at the strongest Lindblad resonances. So just a reminder that the Roche limit is the distance beyond which you can start having accretion. But inside this limit, the tidal forces from the Earth are too strong so that you cannot accrete, form bigger aggregates inside this distance. So the physical processes we include in our model for the Roche interior disk, we include its viscosity, so it's going to spread onto the planet and lose mass. But conversely, as material spreads beyond the Roche limit, the material that goes beyond that limit is going to be able to start to aggregate and form new objects that we add to the n-body portion of the code. And as I mentioned, the inner and outer disk interact with the strongest Lindblad resonances, with the main effect being that the moonlets are going to recede away from the disk, while the inner disk is going to be confined inside the Roche limit. So I'm going to show you a typical simulation with the initial conditions here of an inner disk with 2 lunar masses and an outer disk of 0.5 lunar masses extended towards 6 Earth radii. So you're going to see the accretion of the moon going into three consecutive phases. In the first phase, you accrete very rapidly all the material from the outer disk in less than a year, while the inner disk has been confined inside the Roche limit and is slowly spreading in the second phase until, after several tens of years, material eventually reaches the Roche limit and starts producing new objects that continue the accretion of the moon and also serve as a relay. I see that my movie has stopped here, so I'll try to reload it. There you go. In the third phase, the accretion of the moon continues in the third phase from accretion of the material from the inner disk. And even though the moon is too far away here to interact directly with the disk, the moon is interacted with objects formed at the Roche limit, which themselves are interacting with the disk and serve as a sort of angular momentum relay that eventually cause the moon orbit to expand further away. So here on this graph, you can see the evolution of the mass of the larger object in our simulation. This is the solid line. And while the dashed line is the fraction of its mass that is composed of objects accreted from the Roche interior disk. So you can see here the three phases. In the first phase, you accrete only the material from the inner disk. A second phase where you need to wait for the inner disk to spread back to the Roche limit to start producing new objects that eventually continue the accretion of the moon, where you see here the fraction of inner disk material expanding toward about 60%. So what would be the resulting moon structure for such an accretion process? Well, first of all, you're going to accrete all the material from the outer disk and form a sort of a lunar core and pile up on top of it all the material from the inner disk. The obvious question after that is the amount of mixing that you would need, you would later get between those two layers. So just a few statistics, the global results. We performed about 50 simulations with various disk masses, outer radii, initial distribution of mass, etc. And the average properties of the moon after 1,000 years were, first of all, we successfully reproduced a lunar mass object. The semi-max velocity of the moon is substantially larger than what was found in N-body simulation, pure N-body simulation. This is due to the interaction at Lindblad resonances plus the scattering of moonlet that transfer angular momentum to the moon and expand its semi-major axis. The accretion timescale is now of an order of 100 years. This is due to the confinement of the inner disk by the outer object and the fact that this disk spreads very slowly. Finally, the mass fraction of inner disk material ranges from almost nothing to add up as more than 60%. So what our results imply? Well, if you get an accretion timescale of 200 years, this timescale will be compatible with the estimated timescale needed for equilibration between the composition of the prolunar disk and that of the Earth. And also, the three-step accretion implies that potentially equilibrated material from the inner disk that could resemble the composition of the Earth would be accreted last. And as a rough example, a one lunar mass object with 60% of inner disk material will represent a 460 kilometer deep Earth-like outer layer, which is compatible with the approximate distance where we assume that the Murray basalt has been formed. So if you want more details on this work, all the results have been published in the papers in ABJ last year. So now regarding the moon's initial thermal state, what we did is that we extracted all the parameters from a given simulation, extracting all the collisions that lead to the formation of the moon, so the mass of the impactors, the impact velocity, the position of the impact. And what we do is we reprocess the simulation in a second time by focusing on the thermal energy deposited by each of the impact onto the surface of the moon. So this is only a preliminary work. I'm going to show you here an example of what an accretion, of the evolution of the temperature of the growing moon, average of the longitude. So the color here shows the temperature of the moon. And just to give you an idea, to be subsolidus, the material in the inner half of the moon must be smaller than 800 K, which is like the blue color. So it seems that even though this is still preliminary work, we would be able to form a moon that is not completely molten initially. So for future work, we need to improve that thermal code because for the moment it doesn't include the latent heat that will be deposited in particular, but the hot material from the inner disk. And also we only include for the moment the heating inside of the isobaric core. We also want to study, for the first part that I've showed you, we want to study alternate models of the prolunar disk. In the model that I've showed you, we used a model for the inner disk that is a well-mixed disk, meaning that the vapor and liquid fraction are completely mixed together and evolved as one ensemble. But it has been a paper by Ward, a recent paper by Ward showed that the disk may actually be layered, while the magma being in the mid-plane and surrounded by a vapor atmosphere, and these two phases could evolve separately, and also they're going to be it's going to be necessary to track the vaporization of the magma and the condensation of the silicate vapor, and this should affect drastically the dynamics of the evolution of the disk. Also, we want to, so last year two important papers were published that were studying new kinds of impacts, of moon-forming impacts, mostly the larger impactors by Robin Knupp, and another type of impact involving high impact velocities on a fast-rotating Earth by Chuck and Stewart. These disks generally produce more compact and it's actually more massive disks with more vaporized material that should affect the accretion dynamics. And also, if we have hotter material in the inner disk, that should affect also the moon's initial thermal state. And I think that's all. Thank you.
Hey, thank you so much. Okay, now's the time to type your questions in if you have any for Julien. In the meantime, Julien, let me ask you. So why does most of the heating of the moon seem to happen during accretion happen around the equator?
Yeah, as you can see in the movie, you see that the portion of the moon that gets the more heat seems to be around the equator, and this is due to the fact that the moon itself, when it's forming, remains on an orbit that has a very small inclination and small eccentricity, and also the particles that collide with the moon are issued from the inner disk, so they originate into the midplane, so they also have a small inclination. So basically, you have two bodies colliding on small inclinations, so that most of the bodies collide with the moon around the equator, which has implication because I don't think we see a signature of more heat being delivered onto the moon at a specific location like the equator anymore. So I don't have a strong feeling of how that would impact the internal structure of the moon, but I think that's an interesting insight.
Okay, very good. Well, we are actually right on